Section 4.1, solving polynomial equations and applications. This is the second day. By the end of this lesson, we can define the term I as an imaginary number, define the complex number set, and give all solutions to a polynomial within the complex number set, and use the substitution method to solve complex polynomial equations. All right, so far we have only talked about real solutions to polynomial equations. Now, imaginary numbers are multiples of I, where I is equal to the square root of a negative number, or I squared is equal to -1. So this is a definition that mathematicians have come up with to create a new number set, right? So these are imaginary numbers, right? These like a square root of a -1, right? And this is natural, integer, rational, and real. So these were all the numbers that really made sense to human beings initially, right? Because these are actual numbers that we know, right? Now, a complex number includes a real portion and an imaginary portion. That's what we see right here. Complex numbers are combinations of real and imaginary numbers and can be written in the form of A plus BI. So A and B are your real numbers. I is your imaginary number. And so together they make the complex number set. And that complex number set includes real, rational, integer, natural, imaginary, and in fact irrational as well. Recall, a polynomial of degree n will have n roots. These roots can be real, complex, or a combination of both, right? Now remember, this is x to the power of 3, so there should be 3 distinct roots. All right, so we're going to find these roots, but instead of just finding the real roots, we're going to find complex roots, right? And remember that complex roots can include, if we look up here, complex roots can include real roots, right? So, okay, so what we'll do here to solve this, we have to, as we've seen before, we take this x cubed plus x squared plus 8x minus 10 is equal to 0. Okay. We look at it quickly to see if we can factor this very easily, like factoring by grouping. I can't see that as being a possibility, so we need to use factor theorem. We look at -10. What are the possible values? What are the possible factors of -10? Well, that's plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. We'll start with the most easiest, right? We're going to try 1, right? That's always your starting point. Let's see. Let's see if 1 works. Well, 1 cubed is 1. 1 squared is 1. And 8 times 1 is 8. So 1 plus 1 plus 8 is positive 10. So this portion right here is positive 10. So 1 cubed, 1. 1 squared, 1. 8 times 1 is 8. So then we get positive 10 here, minus 10. All right, looks like 1 is a 0 here, right? Which means that this cubic here can be factored using x minus 1. So x minus 1 is a factor. And if x minus 1 is a factor, that means this cubic can be factored using x minus 1. That's my k value. And I set up my synthetic division. Again, you could also do this with long division. Synthetic, I think, is a little faster. And we get 2, and then we get right there, that's another 2, right? And that's 10, and that's positive 10, and we get a remainder of 0, which makes sense because x minus 1 is a factor. All right, so this then gets factored into x minus 1, and then we have x squared plus 2x plus 10 right there, and that is equal to 0, right? So I've basically taken this cubic and I factored it into x minus 1 and this quadratic trinomial that we see right here. Okay, so I don't see two numbers that multiply to give me 10 and add to give me 2 right off the bat. So I'm like, okay, well, I know that x minus 1 has to be equal to 0. Sorry guys, brackets are not necessary there. So that means x is equal to 1. All right, I've got a real solution to this cubic polynomial equation. Now what I'm going to do is I'm going to set x squared plus 2x plus 10 has to be equal to 0, and I'm not going to waste any time. I'm going to go straight into my quadratic formula. So negative b plus or minus b squared. So that's 4 minus 4a is 1, c is 10. All right. All over 2a, so that's 2. Then I have x is equal to negative 2 plus or minus, and then here we go, negative 36 over 2. Now in the past you may have stopped, however, you're like, oh well, that's not going to be a real root, and so I'm not going to evaluate it. But I'm asking for complex roots as well. So what I'm going to do is I'm going to say x is equal to negative 2 plus or minus. And remember that negative 36 is the same thing as saying 36 times negative 1, right? All over 2, and then x is equal to negative 2 plus or minus. And this one could be, you can split up the square root like this, all over 2. So that means x is equal to negative 2 plus or minus 6. And then the square root of negative 1. Remember, the square root of negative 1, I previously defined that up here. Square root of negative 1 is just I. So divided by I, everything all over 2. So then x, well, that's a horrible x. Let me change that. X is equal to negative 1 plus or minus 6i. Okay. Remember, this has a degree 3, which means it has 3 distinct roots. So one of these roots is real, and 2 of those roots are complex. So therefore, I'm going to give my x values, right? So x is equal to 1, that's my real one, and my complex ones are negative 1 plus 6i and negative 1 minus 6i. So 3 roots, all of which are acceptable in the x is equal to complex number set of solutions. Now, if we were to graph this function, right, we would only have, it would only pass through the x-axis at 1. Remember, these are complex numbers or imaginary numbers, and on a Cartesian plane or on an xy graph, we only graph real numbers when we're using the Cartesian plane. Specifically, traditionally we do x and y. Now there are possibilities of graphing using imaginary numbers, but we're not going to look at that. Okay, here's the next little thing. A quick little trick. Sometimes it can be helpful to introduce a new variable to solve for a more complex polynomial equation. Well, this looks like a beast, right? Like you've got this 2x squared plus 3, then that squared, plus 5, 2x squared plus 3 minus 14. All right, so let's just simplify this. Okay, we need to find all the possible values of x. All right, so we're going to say let a equal to, again, I shouldn't be putting brackets where they're not necessary, 2x squared plus 3. So anywhere I see 2x squared plus 3, I'm just going to write in a. So then a squared plus 5a minus 14 is equal to 0. That's pretty easy to factor. That's a plus 7, a minus 2 is equal to 0. Right, well, what does that tell me? That tells me that a plus 7, so therefore, again, zero product rule, a plus 7 has to be equal to 0, or a minus 2 has to be equal to 0. Now I can input my other values here, right? So instead of a, I'm going to write therefore 2x squared plus 3 plus 7 is equal to 0. Remember, I'm going to put this in brackets here just so you know that this came from the a. I resubstituted that back in. So 2x squared plus 10 is equal to 0. 2x squared is equal to negative 10. X squared is equal to negative 5, right? And so x is equal to plus or minus the square root of negative 5. Well, that just is x is equal to plus or minus the square root of 5, I. Okay, so I've got two solutions here. Then I have to go over here. A minus 2 is equal to 0. So again, 2x squared plus 3 minus 2 is equal to 0. 2x squared plus 1 is equal to, oh, I think, did I make a mistake here? No, this is good. 2x squared plus 1 is equal to 0. Then I get 2x squared is equal to negative 1. X squared is equal to negative 1/2. Right, and then again, I'm going to take my plus or minus square root of negative 1/2, right, and then I'm going to have just basically x is equal to the plus or minus square root of 1/2 I. All right. So my possible values for x that solve this. And it looks like I only have complex solutions here. So plus or minus square root of 5i and plus or minus square root of 1/2 I. Now take a look. You have 1, 2, 3, 4 solutions. And look at this. This is 2x squared plus 3, then squared, which means in total, this was going to be, if I expanded this and simplified, this was going to be degree 4. And if it's degree 4, that means it should have 4 distinct roots. And we see that that's what we come up with. We come up with 4 distinct, but they are complex roots. Okay. Homework is on the handout attached. Thanks for watching.